When we measure different quantities, if we measure mass, for instance, we have units such as grams or pounds. When we measure length, we have meters or inches. When we want to measure the amount of something in terms of the number of particles that are present, we have different units that we can use as well. And probably most familiar to many people are dozen. Say we get a dozen eggs, or we have a dozen tickets to a show. Something of that nature means that we have 12 of that item. If we order things in bulk, we might order them by the gross, and the term gross means 144 of something. Well, in chemistry, due to the fact that the particles that we deal with are so very tiny, we need to work with extraordinarily large numbers of those particles for them to be on a scale where we can actually manipulate them and measure them with conventional instruments for mass, for instance, like the balance, and to be able to measure in grams. And so the number that we use is extraordinarily large, and the unit that represents that number is what we refer to as the mole. A mole of something refers to 6.02 times 10 to the 23rd power of that item. And in scientific notation, that number doesn't look too formidable, but when you write it out in long notation, 602 and 21 zeros after it, it is an extremely large number. This number, 6.02 times 10 to the 23rd power, is known as Avogadros number, named after Amedeo Avogadro, the Italian physicist responsible for deriving this number. And this is a number that was mathematically determined based on observations of gases and the volume that gases occupied under similar pressure and temperature conditions. And thus it bears his name, and it is a constant. Usually we just use the 3 significant digit version, 6.02 times 10 to the 23rd, although you can find versions that present as many as 7 significant figures. Now the nice thing about the mole is that in terms of determining the mass of a formula or a given compound when we're working with it in the lab, we can calculate the mass of 1 mole of that substance the same way that we calculated the formula mass, by simply looking at the formula for the compound and using the atomic masses from the periodic table, find the sum total of all of those elements and however many there happen to be in that given formula. So calculating molar mass is exactly the same as calculating formula mass. The only difference is the units in which that mass is expressed. Now, molar mass, again, can apply to individual molecules, atoms, ions, whatever the particle happens to be. And so if we take water as an example, we take 2 times the atomic mass of hydrogen, which is 1.01 from the periodic table. 2 of them would be 2.02. Add to that the atomic mass of oxygen, 16.0. And rounding properly with the addition, we get 18.0. And again, notice that the units are not atomic mass units anymore, but they are grams per 1 mole of water. For sodium chloride, sodium from the periodic table has a mass of 23.0. Chlorine has a mass of 35.5. One of each. When we add them up, we come up with a molar mass of 58.5 grams per mole. And even a substance such as oxygen, which has the molecular formula O2, looking up oxygen, we see that it has a mass of 16.0, but oxygen in its natural molecular state is a diatomic molecule, so there are 2 atoms of oxygen, and thus the molar mass of molecular oxygen would be 32.0 grams per mole, 2 times the 16.0 that we take from the periodic table.